Yeah. That's okay, I think. Okay, so I think we can begin. Welcome to this Zoom session dedicated to the study of Novae at various wavelengths. Many of us have acquired spectra of Novae in the visible range or near UV, near IR wavelengths, say from 3,300 to 10,000 angstroms. And we try to understand them at different stages of the phenomenon, evolution. And Steve was of great help to us since 2012. But beyond the visible, the nova phenomenon manifests itself over the entire range of the electromagnetic spectrum, from gamma rays to radio domain, providing essential information for the understanding of the phenomenon. If for us UV or near IR spectra presented in publications pose no major difficulties to decipher, the situation is, I think, quite different at the more extreme wavelengths. I'm thinking to X-rays, gamma rays, radio. And this is the reason why I ask Steve Shore once again to help us to understand the information presented in these publications and the importance of the studies in extreme wavelengths. Steve will take the talk, and after we shall have a session of questions and answers. You can use the chat in order to propose your questions, or we'll have also or taking part to the discussion after the talk given by Steve. Thus, now I give the hand to Steve. So I think you can go on, Steve, when you want.
Okay. First, thank you. I'll try. All of you are going to have to be very patient because some of this will get a little bit technical, and if anything doesn't make sense, just interrupt. I don't want this to be any kind of grand lecture, okay? The thing that's important that I want to stress is that what you're doing in studying Novae is looking at a unified phenomenon. It's really important to keep that in mind because every wavelength region informs other wavelength regions. And all of this is just with photons. So in one sense, it's stretching to the max the kind of physical information you can get from just studying spectra. There are a couple of terms I also need to get across. The first is that when somebody says spectrum, you should ask them, which wavelength region are you talking about? Because in the radio, a spectrum has what you would call a resolution of 2, okay? That when you're dealing with a spectrum, you're basically dealing with a spectral energy distribution. When you go to higher wavelength, you always lose resolution. It has to do with the nature of the detectors, with the optical systems, with the intensities of the sources. You can do, for example, genuine spectroscopy in the radio, but in Novae, the vast majority of the emission is from continuum processes. The same is true when you go to very high energy. So the two extremes are really energy distributions, where in anything in the middle range, so going from the infrared through the X-rays, you're talking about genuine spectroscopy. And the approaches are completely different in the sense that one of them contains dynamical information and the other is merely energetics as a function of time. Okay, so that's just to put things in a kind of general perspective. So to start, I hope you can see the screen.
Perfect.
Yes, nice.
Okay, so I have to put this up because you really should understand that there are many people involved in understanding these things. And I just want to acknowledge that anything I'm going to be saying is backed up, is based on the sweat of a lot of people. Those who are principally involved in the different wavelength regions are Paul Kuhn, who's UV and Grissom on Swift, Kim Page, who's the one who keeps everybody up to date on the development of X-rays from observed systems. Teddy Chung and Pierre Jean are in the ones who are the principals for Fermi, in part because Teddy happened to be on the satellite at the time when V407 Cygni went off in 2010. Jordi Jose is one of the most energetic in this field in trying to understand the fundamental physics involved with nova explosions. And Ulissi Munari, some of you know, who's involved both with photometry and spectroscopy, and has the advantage of having in his backyard a 2-meter telescope within a shell spectrograph. The top of the list is my closest collaborator, but also somebody you should all get to know from her papers, and that's Elena Mason. And obviously the bridge is Francois, who I thank sincerely. Others are those who were stupid enough to do their theses with me. And the last, but definitely not least, are all of you who, out of sheer interest, are keeping this alive in a world that's becoming progressively professionalized and quantified. So I'll leave the political comments to the end. So let's get started. I'm starting with the X-rays because you might think you can't see them. It's not quite the same as saying you're going to pull a Superman and be able to have X-ray vision, but X-rays are an indication of thermal phenomena involving very deep gravitational fields or nuclear processing. And so just to get things started, let me explain something about how a nova happens, because this is one of the reasons why it's so important to understand the X-rays, whether you can see the X-rays directly or not. The first thing is the trivial statement that's parenthood, that novae are degenerate objects that accrete in binary systems reach a critical pressure at which a thermonuclear reaction triggers. Depending on the composition of the environment, you get different reaction sequences, but the essential point is that when you reach a threshold to have sufficient thermal energy in the ions, meaning accreted hydrogen and helium, those undergo thermal reactions, capture reactions with background nuclei, and the only ones available, the principal ones at the end of stellar evolution, are helium, carbon, nitrogen, oxygen, neon, and magnesium, maybe some silicon, the general products of core nuclear burning. So when you strip the star, when it's finally gotten to the point where it's sufficiently compact that it reaches what would be an ordinary massive white dwarf if the little bugger were not in a binary system, it becomes the equivalent of a trash pile when the companion starts to transfer mass onto it. For that to happen, you either have to have literally this white dwarf immersed in a background, so something like a wind, which is one class of these, or you have to have it sufficiently close that in the course of its normal evolution, the companion will reach its tidal limit. Getting the systems in that state is somebody else's problem for the time being. But we know that novae are continuous with cataclysmic variables, that those are defined as mass transferring systems in which you have a white dwarf that's accreting, sometimes a neutron star, sometimes a black hole. But in this case, it's something much simpler. It's just the accretion onto a white dwarf. Now, of course, the gravitational field of the accretor, of the gainer, is so high relative to a normal star. It's about 4 orders of magnitude higher than the sun. The pressure at the base of the accreted layer is this critical value at which you trigger the reactions is going to be reached much, much more easily than it would be if you were dumping stuff onto an ordinary star, which also, not being degenerate, would heat up and expand. The thing that's important about the dwarf is that it's degenerate, and so you can pile this material onto it, and the layer will radiate, but the layer is on the outside, so it can radiate. And as you're piling it onto the lower layers, those layers merely compress. Even if they heat up, that energy can be radiated away, and that's where you see the X-rays for the first time, okay? That's why they're so important. The indication that you have an accretion process is, in fact, the presence of the X-rays. Now, the fact that we can't see them from the ground directly doesn't mean that we won't see the evidence of their presence. So, for instance, if you're accreting from a wind, then the X-rays are going to have to penetrate the wind in the process of escaping from the system. That sounds awfully anthropomorphized, that the damn thing is radiating. Space is on the outside of the wind. There's a density change. There's a density gradient through the wind. And so the photons are simply escaping, but they do run into things because there's a finite cross-section for photoionization. And so you will get the formation of some very, very highly ionized species. And that's typical of what you see in symbiotics, that you have both extreme ultraviolet, which means above maybe 30 or 40 or 50 electron volts, and X-rays, which means above like 100 electron volts or even higher. Okay, so the presence of those lines is indicating that there's an accretion process going on that's radiating. Around classical novae, if you've got a disk in a compact system, you won't see those. You'll pick these things up as X-ray sources from old sky surveys like ROSAT. But otherwise, you're not going to see the direct indication of that emission. Okay? Now, the triggering occurs not in this layer that's radiating the X-rays, but in a deeper layer, much deeper. We're talking in depth. It's about the equivalent of, accumulating Europe onto a white dwarf, maybe a bit more. Europe plus Asia. So about 10 to the -6 or 10 to the -5 solar masses, depending on the mass of the white dwarf. Once that trigger starts, it literally explodes. And by that I mean, you get an initial pulse, which comes from the very rapid crossing of a threshold. It's essentially a phase transition. You won't see that. This is very deep in the envelope in terms of its optical depth. But what will happen, because it can't radiate that energy away, is that the layer will start to convect. In other words, it turns turbulent, it mixes, which means that the material that was lying above, that's hydrogen rich, is now being brought down into a region that's dredging up material from the white dwarf. The most important step in understanding novae was in the 1960s, when several, especially Starfield, realized that what has to happen is material that becomes an effective target, carbon, nitrogen, oxygen, those that have very high capture cross sections, which we already know because on the main sequence, if you don't have proton-proton, you have CNO. And it doesn't take much to transit between those two because the CNO has a much higher, much higher temperature sensitivity. So we all have some proton-proton, you'll have some capture, but that's nothing. What's happening instead is when the CNO starts, it goes into the equivalent of a forest fire, which ultimately becomes a deflagration. That as this convection continues, you drag material down from the region that's accreting and dredge up the material from below. So all of this is being mixed up. In addition, what we know now is that you have a layer between these two extremes that's mixing in what we've called a carburetor, that it's essentially the same thing that happens in an ordinary engine that runs on gasoline, that you have a chamber in which you pre-mix oxygen and fuel, and then you ignite it so that you're sort of pre-mixing the material that's going to explode. This is what's happening for 1,000 years or 10,000 years during the run-up to the explosion. And all of this is again signaled by the X-rays that you see outside of the explosive phase. Okay? The whole process that I just described, this buildup of thousands of years, which may be a hell of a lot faster, we'll get back to that later, is completely undone in the space of about 5 minutes. That this deflagration becomes so intense, the mixing is so rapid because it's driven by buoyancy, and the gravity of the white dwarf is so high that the buoyant timescales are extremely short, of order thousandths of a second, that can mix regions of kilometers in size over this whole white dwarf, which itself, remember, we're talking about something which is really compact. Okay? This layer that we're talking about is a couple of 100 kilometers thick. That's about the same as the envelope of Jupiter, if you want to think about depth of a region on an object that's not much bigger than the Earth. So the timescales are all incredibly accelerated. What's happening in that process is the energy that's being released drives the reaction even faster. And you have a front that begins propagating outward, consuming progressively more of the accreted layer. Once that reaches the sound speed, once that expanding front finally reaches the critical step and turns transonic, that layer blows. Okay? That is the point at which we actually see the nova. That's the beginning of your part of the event. Because up to that point, the only thing you would have known is that there was something accreting that was radiating in the bluish part of the spectrum, and there were lines that indicated high temperatures. Okay? So, this is an example of a light, an object that's current. LMC 1968 is a recurrent nova with a recurrence time of about 4 years. It's one of a very small class of extremely rapidly repeating systems, which is the other thing to always keep in mind whenever you're talking to anybody, that these things repeat, that they're hydrogen bombs, but they periodically blow. Maybe the word periodic isn't a good one there. They, on some kind of repetition time scale, they repeat themselves. I'm showing this because this is current with the SWIFT satellite. That SWIFT is a rapid response system that was built originally for gamma ray bursts, but it has the ability to slew from one part of the sky to the other in mere seconds. And because it's a very flexibly schedulable instrument, it can be observing in the X-rays and in the UV, essentially simultaneously. The light curve that you see at the top is from the X-ray telescope. This is in the bands from about 0.3 to 10 kilovolts. The definition, and now we get to this SED business, the definition of sources is the following. If you have most of the energy coming out above 1 kilovolt, you call it hard, or what in the literature in the 1920s was called penetrating radiation. If the energy is below that level, you call it soft. The distinction between these goes back to what I was just talking about. That's why I spent so much time on the thermonuclear runaway. The hard source is not the nuclear source. You can't get those temperatures and those energies from simple nuclear reactions. This is something that requires hydrodynamics. It requires shocks, velocities of thousands of kilometers per second, not thermal velocities of 100 kilometers per second. Okay? I just want to emphasize this, that when at the beginning here, the energy is, this number is above 1. This is a shock. It's the initial expansion of the ejecta, including all of the garbage that's running into all of the other garbage in the ejecta. So again, I'll get back to that, but I just want to emphasize this point, because once the energy is concentrated in the so-called softer region, that is an indication of nuclear processing. And this is the other part of the nova explosion that I want to emphasize. The nova is a passive event after the explosion. What happens with the ejecta, everything that you see for a classical system that's expanding effectively in vacuum, is driven not by internal processes, but by its covering of a central object. The easiest way to think about this is you see clouds in the sky because the sun is shining and the light is reflecting off the clouds. Okay? No sun, you don't see the clouds unless you go into the infrared, and that's cheating. Okay? Because they're hotter than the background or colder than the background, and so you'll see differences. But here, when you're looking in the UV or when you're looking in the optical, that's not an intrinsic process at all. Now this is a difference for those of you who might get interested in observing supernovae, and I know some of you have. A supernova is different. It's the equivalent of a meltdown. It is Chernobyl, that you still have an active radioactive source within the ejecta. The reason the nova explodes is because you created radionuclides like oxygen-15 that have very, very short half-lives. But when I say short, I mean literally minutes. Okay? When those decay, the energy that they release is what's powering the explosion. But once they've decayed, they are not powering the ejecta. In a supernova, you're creating very heavy radionuclides, even transuranics, that have lifetimes of days to years and are incredibly powerful because they're alpha decays and also powered by gamma. So you create, and specifically nickel 56 and cobalt 56 and iron 56 as the byproduct at the end. And all of these that go through these different decays are all massively produced during the nucleosynthesis because of the shock that actually goes through the envelope of the star that's then ejected. Okay, so those don't give a damn about what the central object is radiatively. They are self-powered, and their behavior is fundamentally different. Here, you're seeing something that's just clothing. And eventually, it's first wearing the equivalent of a fur coat, and then it's wearing the equivalent of summer pajamas, and then it's nude. You know, that at the beginning, the only thing you see is this very optically thick surface, and then you see a much thinner layer, thinner in the optical sense, that has a sort of pseudo photosphere, but I'll get to that in a minute. And then you see right through it. And you're seeing right through it is here at the end. Okay? What it means to have this peak is that you've gotten it to be thin enough so you can see the X-rays, but the X-rays haven't yet turned off. So the ejecta at the beginning here, this rise, are optically thick even at this energy. When they turn less opaque, you see the central object. So this rise is telling you about the way that this fur coat is thinning out. But once it's sufficiently thin, this interval, when you see the soft source, is the period during which the central object has residual nuclear burning after the explosion in depth. So this is probably the best example of the turn on I can show you, that you go from effectively nothing to a source that you can see. And during that phase, you go from an extremely hard source, which is here, where you're just seeing a shock, to here, where you're seeing the nuclear source. Okay? This is really important. This turn on is not that somebody is pressing a button and making the source get brighter. It's simply that you're seeing through the ejecta. Okay? Again, I hope this is making sense. The part on the bottom in both of these plots is the near and sort of middle ultraviolet. And the thing that that's showing is it's boring. I mean, look at it. It's just decreasing monotonically over time. This is very nice because what this is showing you is that the ejecta are actually just uniformly expanding. And that the reason this is happening is because optical depth, and this is why I said I'm going to be technical, optical depth is exponential in its effect. So if you change the optical depth by a factor of 2 and it's already thick, you have a big change in the amount of flux that's coming through. Okay? Now, the other part of this is that it's being irradiated from the inside. So if I may, let me switch screens for a moment. I hope I can. Like maybe. Okay. So okay, so I hope now you can see the whiteboard.
Yes.
Provided, of course, I can shift it over. Okay, we will keep hands. We will keep fingers crossed. Great. Okay, so the white dwarf is here. It is in a condition that you would not want to find yourself in. Okay, it has just undergone a massive coronary, and there is no emergency service here. It has simply vomited. And around this source is all of the detritus that it has blown off. And this stuff has been blown off at in a ballistic manner. So the material that's at the outside is there because it was moving faster. And the stuff inside is simply that it was moving slower. So you have here a velocity field that has an extremely simple profile. That is that. So what's happening is that all of this material is originally optically thick. Now, the inner portion, and there is a genuine inner portion, has light impinging on it from the central object. In other words, from that which was an ordinary white dwarf. That radiation is from the super soft source. It's peaking in the intermediate X-rays, and so has energies that are well above 100 electron volts. Now, to remind you, the ionization energy for hydrogen is about 13 volts. That of helium is about 25, just to keep rough numbers in your head. For ionizing helium-2, that is, to get doubly ionized helium, you need about 50 or 60 volts, depending on the excitation. The point being, if you can get to 100 electron volts, which is still on the really soft side, you're going to be able to get to iron 10. Okay? So this inner part is ionized to very, very high levels. And it is somewhere here, effectively a photosphere to this outer material. So this stuff is expanding, and as it's expanding, its effective temperature is dropping. This is the key to understanding what's going on in the first stage. The X-rays are always there. The only question is, what's the reaction of this medium? At the beginning, before you can see the X-rays, this region is completely optically thick and very hot. That's the fireball. That's the initial stage. So that stage where you see just the shock, you're seeing this outer surface. And you're seeing all of the pieces that are slamming into each other because of the way the explosion occurs. It's not, let me make this as clear as I can. This is a mess. The explosion does not occur the way it does in Oppenheimer. It's just the opposite. Nature doesn't have to be efficient. It just has to happen. So different pieces are coming off at different speeds. They're not exactly at the same time. You're not triggering a pre-planned explosion, even if it takes a matter of 100 seconds. At velocities of 1,000 kilometers per second, you have pieces that are slamming into each other throughout the ejecta. Okay? It's a matter of the relative distance that these pieces can cover. All you have to have is a spread of 100 kilometers per second, and this becomes an aerosol of shocks. That, I think, is what you're seeing in the initial X-rays. That's why they're hard. They're indicating temperatures that are above 100 million degrees. But the super soft source is down at about 1 million degrees. And that's optically thick. So as this stuff expands, you have a photosphere that's moving outward, but the temperature at that photosphere, the SED, is dropping. And so suddenly, at some distance away, everything recombines. And all of that light goes from being in the X-rays and the UV into the visible, and that's what you see. That's the beginning of your part of the event. So the super soft, I'm not sure I can do an easy screen switch here, but I can try. Well, it's going to have to be the hard way. So, in the fastest Novae, this one holds the record. It's in Andromeda. 2008 12A has something deeply upsetting it because it explodes about once a year. Almost exactly once per year. The theology in the business is that the thing that determines whether or not, whether a system is recurrent or not, meaning that it does this on human timescales, it repeats on a human timescale, requires that you have a very, very massive white dwarf. There's a limit to how massive the system can be just from mechanical stability, called the Chandrasekhar mass, which is about 1.5 solar masses. Okay, 1.4. I'll be a little more correct for once. But the critical thing is, if you get anywhere near that, the system will trigger much more easily. But more important, and this is where we don't have an answer, and what you guys do is so tremendously important. We don't know how long it takes after this to recover, or what happens during the recovery. In fact, the thing that's striking about this nova, you notice the magnitudes here. This is in the UV, but 20th magnitude is pretty faint, and it's in another galaxy. So you have 1 arc second being roughly 10 parsecs. Okay, so the whole solar neighborhood fits into your PSF. That's not good if you're trying to identify a source. So in this case, what we don't know is what happens when this gets ready to trigger again. Is it that the white dwarf is just so massive that it literally turns off instantly, blows off everything that it had accumulated, maybe even a little more, and suddenly goes back to being a normal white dwarf? It's really hard to believe that, because the insurance companies usually won't cover that stage. So you might think that you're going to have a kind of damaged goods, and we don't understand this. So what we're seeing in the X-rays is the indication that the nuclear source does in fact turn off. It does exhaust the hydrogen that it's accumulated. It doesn't mean that it stops burning. Doesn't mean that the system cools instantly. Please keep that in mind. This is deep in the star. The thermal timescales are decades to centuries. And that's where one of the mysteries lies. So, step 1, the X-rays indicate there's residual nuclear burning, and you see that in the evolution of the ejecta. Okay? That covers the X-rays. Sort of, I hope. So, next stage. This is just to show you again a classical system. This is 2013. This was the second nova that had the claim of ARAS observations, and was the only other nova besides V339 Del that we've observed in a coordinated way in the ultraviolet, X-rays, gamma, the whole shebang, and where your observations have been more than critical in determining what was going on. The thing that you see here is the X-rays rise as the UV, as the optical declines. This glitch is dust formation. I'll try to get to that in just a bit. Just one last indication in Nova V906 Carina, which was one of the brightest in gammas. This just shows that you get the hardness ratio changing over time. No big deal. This is not yet published observation from a thesis at Pisa by Remo Di Giacomo that is a sequence on the Nova CAS 2021 B1405 CAS. This is about 300 days after outburst. The X-rays are on the top. Most of them are upper limits. These are detections, and this peak here is a detection. This is the connection. The line that I'm showing is iron 7. Its ionization energy is like 90 volts. So to see this requires that there be a super soft source. Here, there's zip, nothing. Then, for a couple of days, it shows up and then disappears. And then it shows up again and disappears. And then it stays on. The only thing that can be doing that is you're changing the X-ray illumination. It's not running into anything. There's nothing out there. It's not a process where somebody has turned a flame on in the ejecta. This is a thermometer, or better, a bolometer. It's telling you something's going on in the X-rays. And when you look back, you see, yes, something went on. This thing flared by a factor of 3 in the X-rays. Probably because the nuclear source is unstable. We already know that from other steps. So, the next, we go from the hot to the sex and violence, okay? Gamma rays automatically get you into what's referred to as high energy astrophysics, and a whole other community who, to be blunt about it, generally don't know what is going on, but they like gamma rays. Usually, gammas are produced in cosmic sources by extreme non-thermal processes. For example, the gamma ray emission from solar flares involves the acceleration of particles to relativistic energies. Not temperature, but something non-thermal. In gammas, one sees active galactic nuclei, where again you have accretion around on a black hole, and you get to energies above 10 to the 9 electron volts. So you can get gigavolt or even teravolt energies. So it was really unexpected to people when in 2010, and then later after 2013, the Fermi satellite started detecting gamma rays from Novae. Now, never mind that shocks can easily produce gamma rays. What was really surprising, and what is still a standing argument, is what I'm showing on this slide. These are the first observations of a few Novae classical systems, Nova Cen and Sagittarius, both of which were perfectly ordinary, and you're seeing energies above 100 MeV. As it says in Ghostbusters, you don't expect that kind of behavior from a normal appliance. In this case, it's an indication of non-thermal processes, of some kind of acceleration mechanism that is, in this case, accelerating electrons to gigavolt or higher energies, and which is not that unusual, and accelerating protons also to relativistic energies. When protons collide at high energy, so hundreds of MeV or gigavolts, they produce pions, and the pions decay into gammas, which is one of the ways you can get this. This is called the hadronic scenario. The alternative is synchrotron, that you have relativistic electrons that are trapped in a magnetic field, the same thing that produces the radio emission in the Crab Nebula and in any supernova remnant, that these electrons have been accelerated by some process, presumably by the colliding shocks, and they radiate in the gamma rays as well as in the optical. They can scatter and radiate. So you have two different processes competing. In this field, people literally fight duels over which one of these is going to be the explanation. What's important as a bottom line is the presence of gammas is perfectly expected. There probably are both processes acting, that is, electrons and protons. There may even be some nuclear line emission because of the residuals from the nuclear reactions at about an MeV that go back to predictions from as early as the 1970s. In other words, the presence here is indicating non-thermal processes. It's a window into now the hydrodynamics, not the nuclear processes. So this is something totally separate. The advantage of the gammas is that they're found from, they're measured by a satellite that doesn't go through Earth occultation. Fermi is, it scans the sky completely in a few days. So if a nova goes off and you can get you can get gammas from it, you'll get a pretty good light curve. The problem is a different one. You see all these gray dots, ignore them. Those are upper limits. And the thing that may make you a little nervous is that you've got upper limits that are larger than, that are higher than the detections. That's because of the way the background behaves. This is something you don't have to deal with in the optical, because none of us are naive enough to try to observe novae in the daytime in the optical. Okay? If we were, we would have this problem, that the background would be changing and from one day or 1 hour to the next. The other indication, this is Assassin 18 FV, which is a transient. It's been called a slow nova, but it could be something else. But you see that the gamma rays here sort of kind of track the glitches in the optical. Okay, going to the other extreme, you might think, is centimeter and millimeter. Low energy, so less than 100th of an EV. You would think this is the cold and uninteresting. No, because this region happens to be where synchrotron is radiated. This is where the electrons radiate. So if you have relativistic electrons, they can scatter their own radiation. And that is presumed to be one of the origins of the gamma rays. But this stuff, if you see a non-thermal spectrum, that means you have magnetohydrodynamic shocks, you have particle acceleration going on, and that's in the same wavelength interval as the thermal emission from the cold gas, and just from the thermal emission from hydrogen. This is again where we stop doing spectroscopy and talk about energy distributions. So these are the radio light curves. The top is the optical. This is from a collection by Chumiuk and Sokolovsky and a bunch of others who do VLA observations. The different wavelength regions are here. Time is running on the bottom. These are amazingly simple. They are exactly the same as the X-rays. The source turns on because the opacity depends on wavelength. As it turns thinner, the peak moves to different wavelengths. So you can get an idea of how much gas there is in the ejecta by looking at the way it turns optically thin in the radio. You do not measure anything precisely with this. It is confirmatory. That is, in all of these curves, you see that you have steadily declining optical, sometimes glitching, but that's a different issue. You don't see this in the radio. You won't see this in the radio because this is the stuff that's already optically thin. So it's at the farthest distances. It's already really thin. It's just that radio to itself is very opaque. So next, in the intermediate, there's U. That is the ultraviolet, which is the driver, and the optical, which is what you see. This is something unique. It's the history of the UV in one of the brightest novae of the 20th century, Nova Cygni, V1974 Cygnus, 1992. It was observed by IUE. We will never have this kind of data again. So I'm showing you this because it's really all there is. In the nova was observed in the UV within 12 hours of its being announced in optical discovery, which means we didn't know what to expect. And it was a very bright UV source. You see this is in the wavelength, sorry, this is in the energy region up to 10 volts. So this is a hell of a lot harder than anything in the optical. And for the first 2 days, so from here, this is the 22nd, so here, this is 1 day. And then nothing. And when I say nothing, I mean, you see this little glitch down here? That's not noise. That's all the light that we were getting. All of that came out in the optical. So the UV goes down and the optical is the reprocessing of that radiation. That is the end of the fireball. The recovery takes weeks. And you see that what happens is first you start getting these little windows. These are not emission lines. The spectrum is so dense and so complex. It's these lines overlapping each other and then slowly having them clear out. And as the UV gets brighter, the optical fades. So what you see in the optical is telling you what's going on in the ultraviolet. In the same way that seeing the optical, if you know which lines to use, is telling you what's going on in the X-rays. So it all fits together. Okay, this is what we called at the time the Iron Curtain. It was a political statement, actually, because there was this thing about the lifting of the Iron Curtain, but never mind. So in the optical, when you have high resolution line profiles, the thing you learn from those profiles is the ejecta are not spherical, which anybody could have told you anyway, but we like spheres. If it makes it a little bit more obvious, let me show you one additional screen, which is here. This is an image taken with HST. This is about, I think, 4 arc seconds across. It was taken after the corrective optics. This is HR Dell. The image is from the 90s, and the Nova went off in 1967. This is what the ejecta look like in the forbidden line of oxygen, and also, if it were there, neutral helium. But this is the 5007 line. I think I can convince you from looking at this that the ejecta are not spherical. That's what changes everything. If you have spherical ejecta, if you just have the equivalent of a star, then it doesn't matter which direction you're looking at. So the same nova, if it repeats, will look the same to all observers. If, on the other hand, the ejecta aren't spherical, then it depends very critically on which angle you're looking at. So even though you have the same amount of mass, the same explosion dynamics, all you have to do is change your line of sight. And this is looking across the ejecta, and this is looking down the ejecta. And so they'll turn optically thin at different times. They'll show different behavior in the spectra. Okay? No two novae are alike, not because the phenomenon is different, but because the perspective is different. And this is something that I hope will justify your continuing interest in these, because even observing the same nova from one explosion to another, if it's a recurrent, there are differences. You may not have noticed the subtle differences in the LMC curve in the X-rays, but it's different. It's about 30% different this time than it was 4 years ago when we had similar data. It's not a big deal, but it means that every time you do that, you're getting a different perspective on what is involved with the explosion. So, to continue, and just as a warning, Francois, if I'm really overdoing it, shut me up. Okay, this is what happens in changing the geometry of the ejecta. The left are the actual line profiles. These are hydrogen line profiles from real novae, all in the optically thin stage. So T-Pix, V959 Mon, V339 Del, and V1369 Sen. So these two from 2013, this one from 2012, and this one from 2011. On the right is what this geometry produces as the model. These are not these are not observations. These are models. Just to show you that, you see, all you gotta do is slightly change the angle, like here, between these two. It's the same ejecta, but you're looking at different directions. Okay? The other thing that's very striking that you can do is that during the ejecta expansion, when you actually get absorption lines formed and peaks in the emission, you're seeing those fragments. The thing that's fundamental is those fragments remain forever. If you've watched the explosion of fireworks, you know that the individual fragments just move outward, essentially constant speed, and fade. But they're not, at the beginning, they're not being slowed down by friction from the atmosphere. Here, there's no atmosphere. So these individual fragments are simply absorption seen against the central source, and they're the same things that show up in the optical. This is in the ultraviolet. This is in the optical. By looking at those, we're seeing three-dimensional structure in the ejecta. This is just another example looking across different profiles over time, that as the ejecta thin out, we see more of the fragmentation. The other is something, again, that's new for V1405 CAS, that in the optically thick stage, you see absorption. In the optically thin stage, you see emission. These are on different lines. So they're tracing the same structure. But in one case, it's stuff that's been ionized by the X-rays. In the others, it's ionized by the UV. This is in the early stage. This is in the later stage. These two are different from each other completely in the thermal structure of the ejecta, but they're tracing exactly the same three-dimensional structure. Even more striking, the bottom, and I think this is really just neat stuff. Sorry, these two lines are the same as these. These are interstellar sodium, neutral sodium D. These are the resonance lines. And This is a portion of the ejecta that completely recombined and turned neutral. At the same time, as you see on the iron, only one of these was neutral. In other words, we're even seeing individual ionization differences from fragment to fragment. That points back to the UV. That points back to the X-rays. So we can go backward and forward in understanding what the physical processes are. Then there's looking at these fragments as a function of time. Historically, the top is H. Ardell, the bottom is Novae. This is a new result again from Ramos' thesis. I'm showing you this just to show that it's the same thing. This is just flipped upside down. Totally different nova. 30 years later, having absolutely nothing to do with it. This is not individual ejection events. These are the visibility of fragments that were created at the time of the ejection. And each one of them, and this is why I think this is so important. So please pardon my enthusiasm. Every one of those fragments could have a different history of nuclear processing. You know this. You pick up a rock just on a trail. You know that that rock is not a monolithic entity. It may be metamorphic, it may be sedimentary, but it has crystalline pieces that have different composition all through it. It's not homogeneous. It's simply homogenized to a minimal extent. Okay? One of the things we would hope to find in this is the individual fragments, these individual knots that we can distinguish in the profiles may have different abundances. We don't know that yet. But if they do, that's going directly back to the moment of the explosion. It's exceedingly important because knowing how the nuclear processing works, if we understand it in a nova, we understand it in any process that goes through, any object that goes through this, including the core of a red giant when it ignites helium, including the core of a red supergiant when it ignites carbon, including what happens in the explosion of two merging white dwarfs. We'll begin understanding the inhomogeneity that is inherent in that process. So, the last is the other kind of nova, which is the difference between blowing up in a wind and blowing up in space. The top is ARAS Ophiuchi, the bottom is V407 Cygni. You'll notice that I've put as a comment in orange that I think all of you, I'm sure all of you have been propagandized to the hilt that the most remarkable event of the 21st century is about to occur with the explosion of T Corona Borealis. Nonsense. It's going to be really nice. It's going to be neat. It's no big deal. We've seen it before. The only difference is someone has said it's going to happen on a particular day. And they've actually committed to a time which gets the media really hot under the collar because they have a prediction. Okay? I know this is being recorded, so for posterity, there's a very famous study called When Prophecy Fails. In the 1950s, a UFO group prophesized the end of the world. And when it didn't happen, they doubled down. And some sociologists from the University of Minnesota got to study this group to see what happened after the prophecy failed. Okay? I'm hoping that no matter what the prophecy is, it will happen and you'll be ready for it. But you must and I mean this very seriously, consider that what you're seeing is not unique. It's special for other reasons. It's special because for once, people are preparing for it. For once, it's going to happen in an interval that we can actually prepare for. Okay? Normally, we're scrambling. This time, it's organized. But what you will see is exactly the same thing that you're seeing here. There are two components in this spectrum. These broad lines are from, in this case, H delta, H gamma, and also helium, iron, and hydrogen. Every broad line here has widths of hundreds to 1,000 kilometers per second. Every spike that you see, and look at the correspondence here, every spike is real. Those are forbidden lines. That's because when the flash goes off, the whole environment ionizes. You won't see this in a classical nova because the environment is just space. But this is the wind of the companion. So it's the same thing you'd see in a symbiotic, except in a symbiotic like RR-TEL, it takes years, maybe centuries, to reach this level of ionization because the source is so low luminosity. Here, the source is something like 10 to the 5 solar luminosities, and it's an exploding shock. The X-rays show you that. There's the shock, which is this part, and the nuclear source, which is this part. This is every one of these that's been observed with the SWIFT satellite. So it's the curve that you were seeing before, except now looking at different sources. This is the same source. This is RSO, except two different explosions, one in 2021, one in 2016. The system in one case was seen like this. In the other case, it was seen like this. So it was just seen through the wind. We don't know with T-Core what it's going to look like because of the wind. It could be this, it could be this, or we may not even see it in the X-rays. Okay, another example is that this is the iron 10 line, and this is the tracer of the shock. This is the X-rays in one of these systems, B407 Cygni. Okay, this is an optical line. This is the X-rays. So now, if we don't have the X-rays, if we see the optical line, all we have to say is, yes, we have X-rays. You see, the beauty of all of this is that as we build up the accumulated experience, when the day comes that we don't have a wavelength interval, we'll know what was going on. When HST ceases, there will be no UV in your lifetime. When SWIFT is turned off, we will not have light curves like this again. When JWST eventually ends, we won't have that portion of the infrared. So since we know that the physics is what's producing this, it's not just phenomenology, it's process. As we understand the process, we'll be able to tolerate that loss of information. That is what I'm trying to emphasize with this multi-wavelength business, okay? So the other is this. I wanted to compare the same stage of the expansion between two systems. The white is a classical nova that isn't blowing out into anything. And the bottom is V407, which is one of these in a wind. And what you'll notice is you see the broad lines and you don't see any of the narrow lines. That's the result of seeing the shock in the ejecta and not seeing the effect of the converter. That is what you're seeing in T-Quabor. That's what it's going to look like. You will not see this in space. This is the fireball from a ground nuclear test. You see that it has already structure on it because of thermal instabilities. Those are regions of different brightness. This is about a second into the expansion. It's a couple of kilometers across. What you're seeing here is the expanding shock front. Okay, you won't see this in a nova. This will disappear almost immediately. And the ejecta will then be the individual fragments that you're seeing here. What you're seeing instead in those narrow lines is very much like the Castle-Bravo test or the Tsar. That is, you have here a vapor cloud that's condensing out, but it was ionized by the blast. So the shock is here, the expanding ejecta are here, but this is the effect of the environment. You, as observers, will see lines from this in the optical. This is going to radiate like an H2 region, like a planetary nebula. And it's going to fade just like that because the only thing that's powering it is the blast. So when this is gone, this is simply dropped below the ionization energy. Okay? Okay, I'll skip over that. The last is the infrared. This is because JWST will not be doing this. That is not a satellite that turns on a dime. It's slow and lumbering, and you cannot turn it in a matter of minutes. It has to be pre-planned, and so there are very few observations that will be similar to this. The top curve is one of the most famous novae of all time, DQ Hercules 1934, seen in the optical. The great dip was the formation of dust. This was already understood as an explanation, although no one had a clue why, already back in the 1940s. The thing that you'll notice is that after the decline, if you put an ordinary light curve on top of this, if you can extrapolate right across this as if it never happened. In the infrared, something else happens. This is V705 CAS from 1993, and this is a theoretical curve for explaining what was going on. Okay, one moment. So, what you were forming is dust. That you still have the central source on, you still have the irradiation going on, but now throw some dust into it and it reprocesses into the infrared. And so you get this, that here the UV and optical drop because you're obscuring it. You're blowing smoke in front of it, and the infrared goes up. The evidence of this is looking at the spectrum itself, that we know something about the dust because we see it forming. We can see the infrared. We can also observe in different wavelength regions. It's literally like throwing a veil over the spectrum. The spectrum shows evidence of carbonates and silicates. So it's just the same stuff that you find formed in stellar winds, like Wolf-Rayet stars, and the same stuff that you find in asymptotic giant branch stars. It's just ordinary solid soot. We still don't know how it forms. There are several mechanisms. One is shocks, one is photoionization, and it's probably all of the above. There are lots of ways of getting stuff to coagulate. So again, this is frontier stuff. Even though we've known about it for 50 years, the physical process is not well understood, and it can only be understood by observations at this stage. Some of the ejecta are resolved. So I'll just show you two examples. This is Nova V1974 Cygni. These are models based on the line profiles. These are the actual observations. The remnant of V959 Mon, although this has never been published, was observed with HST, and these are the different wavelength regions. And again, it's a kind of biconical structure. So it looks like this. No big deal. Take this, turn it on its side, and you have Nova Mon. In other words, you can recover this information. So if you know that, every one of these peaks may be telling you what I was mentioning about abundances and inhomogeneities. Again, this is examples of calculating the structures, comparing the real thing with the models. The last is to look at different times and see that once the ejecta turn optically thin, and these are very highly ionized, so they were emphasized, were irradiated by X-rays. One of the last things I'll mention is that when the X-rays turn off, the ejecta do not recombine. So you can see iron 10 in gas whose kinetic temperature is 10,000 Kelvin or cooler. They stay ionized forever. This is not what happens in the wind case. The wind recombines, the lines disappear. These simply fade, but they are forever ionized. The best example of this is the solar wind, that the behavior of the corona, the temperature of the corona determines the wind. The wind expands hundreds of times its radius at the corona. The Earth is over 300 solar radii away, but if you measure the energy distribution of the electrons and protons, they're the same as in the corona. They don't cool. So you're looking at something which is completely out of ionization equilibrium. It is a frozen system. Okay? And then the final thing is the aftermath, where we know there are accretion disks. This is a time sequence of 8 hours with VLT in the near, it's in the region around the calcium line, that these are helium and hydrogen lines. This is the neon from the ejecta of this nova. And you can see that it's varying. You can see the accretion disk and the hot spot. This is just to show you that this is something that you can also do for these systems with your data, that because they're dynamical, the only thing you need is telescope time. So that's it. These individual processes, I hope I haven't saturated you. These individual processes are all linked within one structure. And if there's nothing else, if you're feeling confused, then I've done my job. You should feel confused, because each one of these is giving different information, and usually these communities don't talk to each other. those who are doing gammas are very specialized, in part because they come from an extragalactic community that had concentrated on quasars and BL Lacerites and accreting supermassive black holes for so long that they didn't think stars were interesting. The X-ray community has known for a long time that stars are interesting, but most of the time they're so concentrated on looking at the energetics of the accretion disk that they forget that they can use that information to understand something about the other aspects of the transients. Maybe this will change in the next few years when the transients start pouring out of the Rubin telescope and people have no idea what the follow-up is supposed to mean. So my advice is to start taking a holistic view of what you're doing. Think about this as a window into a way of thinking and not a specific target that is so important that it should dominate your lives, that when you're doing your observations, follow the Greenpeace motto, you know, act locally, think globally. Act on an object, think physics. Okay, I'll stop there. That's probably enough.
Thank you very much, Steve. I think we shall have, we need some time to digest all the information. But now, if participants have questions, you can ask your questions to Steve. No problem.
I'm afraid that
some.
Go on.
In fact, as you said, Francois, I think we need that. Yeah.
Your sound
is. Oh, sorry.
it may be better if you turn off your video.
Okay. And in this way, is it better?
Yes.
Yes. Okay. Yes, I would say that, as Francois mentioned, for myself at least, I will need some time to really integrate all the information you give us, and questions may arise with time. And so I was wondering if there is a way to ask you questions after this Zoom session, in fact,
Absolutely.
in a asynchronous way.
Yes. Francois will distribute my email.
Yes, okay.
I do answer. There may be a lot of typos in it, but it's just two fingers. But yes, with pleasure.
Thank you very much.
I realize that this is a little bit like going to a 20-course dinner and trying to consume it in a half hour. So I do understand. The reason I was doing this was not to pass on the specifics, but to just give you an introduction to the way of thinking. So anything that might trigger from this, anything that I can help with, just write. It'll be a pleasure.
Steve, this is Sean here. A question about the role of the accretion disk in all of this. I'm always confused about that. What's happening on the stellar surface? What's happening in the accretion disk? Is it optically dense?
Okay, first, the disks are optically thick. But when you say that, it depends on the wavelength region. You see, that's the problem always. Optical depth is a relative thing. You know that because you've all had your teeth x-rayed, right? So you know that at an energy of like 50 volts, your teeth are optically thin, but you don't see through them, hopefully, with your eyes, right? So it's the same thing with the accretion disks, that the outer portions are actually very optically thick because they've recombined. The inner portion where you're getting the X-ray emission, because it has the highest velocities and the highest relative velocity, so you get stuff slamming into itself and heating, and you get the actual accretion onto the white dwarf. That region is optically thin in the X-rays, at least part of it. The accretion disk is the way that the material is delivered to the star. That there is nothing that goes through radial info. These are binaries. The stuff is coming in with an angular momentum, always. And so it cannot fall straight in. And in the circulation, it slams into itself. It generates turbulence. It generates a sort of friction, and it eventually winds up on the central star by processes that we've been trying to understand for 50 years. So step one, part one as an answer is, I don't know. We know that the disks are there. We know that they are central. We know that they drive mixing. We know that they are the source of the material transport. What we don't know immediately is whether and how they survive the explosion and or reconstruct. We know they must reconstruct because, and this is why I mentioned the M31 recurrent, that nova tells us that the accretion can virtually instantly restart. Whether it restarts to something that the cold start would show, or whether it's a hot start, we don't know. So you can think of it as the accretion process. And I don't mean this as a joke. The accretion process is the same thing as would happen if in a forest fire, after the forest has calmed down and you think that it's all over, because anything that could burn presumably has burned. If there's a little bit of extra wind, it can stir up the ashes, which are still hot enough, and it starts up all over again. Okay? So what happens when the accretion restarts? Is it restarting onto a generic cold white dwarf the way we calculate it in our models? Or is it starting onto something which is in a damaged state? We know that the accretion rebuilds because we see that in the recurrence. We can see the disk rebuilding, but we don't see the disk becoming stable. So, third part of the answer, some parts of the disk are going to be optically thick and some parts optically thin, and that's going to change over time. I think the biggest problem that we're facing in understanding this and related phenomena, and that includes mergers and mass exchange in ordinary binaries, is understanding what happens at the interface between the accreting material and the central star. It's the same obsession that engineers have when they're designing cars and wings. It's called the boundary layer, the bounding region. The outer disk, we know what that's doing. Some of my colleagues might get a little upset with my saying that, but we've known what's going on out there for at least 30 years. We have no clue what's going on in the inner drift, because that's as hard for us as it is for the engineers. So the role that the accretion disk plays is the central role of delivery. No disk, No accretion.
Question.
Really simple.
We have also magnetic white dwarfs with
Sure, but
stations
if-
near
Francois,
the poles.
that's not the same thing as having somebody say in baseball raising their hand and catching the ball on the fly. Okay, the magnetic field is a magnetosphere which is bounded by the disk. The disk is still controlling the accretion. The accretion onto the star, you're right, is controlled by the magnetic field. But it isn't that the field is reaching out into the interstellar medium and grabbing things. And as soon as you have the companion, even if the material is gliding along the field, it still feels a strain. And not all novae are sufficiently magnetic for that to dominate. Those have to be polars. In fact, one of the things that it's again the inner boundary. If you want to say that it's a magnetosphere disk boundary, yes, I'll agree with you. Those not only exist, but they are forefront calculations. The same problem that you have with K-Tauri stars, that you have a dynamo on the star, and it's still surrounded by some of the protostellar material in the disk. And we know, like Fu Orionis objects, we know that these things accrete in bursts, and they must be accreting in part on their magnetic field lines. What we don't understand is the way that that field threads the background disk. We know the disk is dominant over part of its structure, and the magnetic field is dominant over part of its structure. We know that because we see X-ray pulsars. But the magnetic fields are much more dominant, much more controlling if we have neutron stars, because the fields are so much more amplified. I hope that.
That's what they.
Steve,
Yes.
to kind of follow on with Sean's question, and this disk, is it, we assume it's equatorial? Is there a tidal locking?
That's, oh dear. You asked the Giga question. I don't know.
Is there a
It should be pretty, it's going to be pretty much within the equatorial plane because of the way the material is flowing in from the companion. But for example, it's going to flop. I think you can think of it as a kind of fuzzed up pizza. There are modes that it can trigger. We also know, and this gets back to Francois's point about the magnetic field, we know that there are systems where the rotation period is not the same as the orbital period. Those are called intermediate polars. So a classic, one of the novae in the 20th century, V1500 Cygni, is a polar. It's an intermediate polar. The rotation period is of order, in some cases, minutes, and the orbital period is hours or fractions of a day. So you have material that's accreting onto the poles, but it's not synchronized. On the other hand, the outer part of the disk will feel a tide from the companion. And that's where the problem comes in, that you have this flowing material, okay? You've got this extended structure, and it's being aligned along the line of centers like this, okay? So this stuff is going around and being accelerated and decelerated as it's orbiting. That does things like creating standing shocks. So things like the hotspot are the phenomenon connected with this. That process is still in the primitive modeling stage. But the observations that I was showing you of the S-curve, so that last slide of the trail spectra, that's where you're seeing it. That there are like 5 different components in those line profiles. One is the disk, one is the stream, one is the hot spot. Then you have the overlying ejecta, which are just contamination. And you have the emission from the chromosphere of the companion. And all of these are mixed up in that profile. You can only sort them out with time. But
Thank
there's...
you, Steve. Steve, I have a proposal for you.
Yes.
A next meeting about equation to the white dwarf through a disk, the accumulation of matter in the envelope, and the conditions for a nova outburst, which may be much more complex than looking at light curves and comparison of light curves and so on.
I hear the irony in your voice. Yes. The wonderful thing is that all accretion disks are created equal. So once you understand what an accretion disk is in, say, a cataclysmic, you understand it in all binaries. It's just a matter of the way it manifests itself differently. And once you know what the magnetosphere is doing in, say, Jupiter, you begin understanding the magnetosphere in the inner accretion disk of an X-ray binary. So yeah, if this is either a threat or an invitation, the answer is certainly yes, if people can stand it.
Yes. I think
one thing, by the way, for those who want to do something fun tonight, fill a sink and drain it. And I mean that as something, not as an analog of an accretion disk, but to see what the processes have to be to get you to move material onto a central object. That the last stage is falling, and that's exactly what's happening at the base of the accretion disk on a white dwarf. The drift inward is from internal viscosity in the fluid. That's what we don't understand. It's a hell of a lot easier to drain a bathtub or a sink than it is to drain an accretion disk in a binary system. But we use the same physical description. So when I said that all accretion disks are created equal, I meant it. The only difference between them is the process that gives rise to the controlling parameters, like viscosity and gravity. I mean, if you see X-rays coming out of your bathtub, you know that something's wrong.
thank you.
It would be like something out of Ghostbusters, you know, you open the refrigerator, it says Thule, and you slam it shut, and you know something paranormal has occurred. But make that flow, instead of being a centimeter per second, bring that flow up to like 500 kilometers per second, and you'll see that in your mind's eye, you can start to see the structures that turn into shocks and the things that are going to turn into heating, and all of the buoyancy effects that are going to govern the three-dimensional vertical structures. Okay?
That. Joe, you want to speak? Do you want to?
Yes.
Yeah.
Yes. I'm not totally prepared to ask this question, so I'm going to ask it in general.
Go ahead.
This is relatively simple. I'm sure it'll be quite simple, because a couple of weeks ago there was an ATEL that mentioned an observation of T Corona Borealis in the microwave region, and that
Yeah.
it was exciting enough to put out an ATEL on it. Did you see it?
I
And
was on
can
it.
you,
I'm one of the authors.
well, tell us then, tell me anyway,
Why is it in
why
the?
it was so exciting to put out an ATEL on. I asked Francois and he didn't know, and I really don't know. So what's going on there that we should be aware of?
The simple answer is it's not.
Oh,
Okay, let me explain. ATELs have several different reasons for existing. One is to get people off their butts because something has happened. You need to let people know quickly that it's happening. Another is to warn people that something might be coming. That is, that you've gone back, looked at something, and you see a change. And the third is that it's not something that you're going to publish separately, but you want it out there because it's a data point that will be useful when the event happens. Our ATEL was in the third category. There was a proposal made to the Atacama Millimeter Array, ALMA, to do an observation as a target of opportunity and director's direct discretionary time to observe T-core bore before the explosion. We weren't trying to get it. We were trying to get a baseline.
mm-hmm.
Since the last time anybody observed this bugger in the millimeter was, or in that wavelength region anyway, was in 2019. The observation shows absolutely nothing of interest, which is really nice. No, it shows the wind.
No, I appreciate that. I understand.
And one of the things that is really difficult to get across to the community, because they're all into discoveries, is that the way you understand something is when something weird happens, but to recognize the weird, you've got to know the normal. And I don't mean that just as a metaphor. If you don't know the baseline, you can't recognize what's changed. That's the whole point of calibration. So what we were doing was putting out the equivalent of a calibration. The fact that the source was detected simply means we're seeing the wind. What we will see is the shock. When the explosion occurs, we're going to get a lot of information about the high temperature part of the shock. Some of those in the collaboration were thinking that we would see masers, perhaps, because you have this pulse going out. It's just the opposite. You're not going to see those. I was hoping we would get a measurement of the interstellar medium because this is a wavelength interval, a frequency interval that includes carbon monoxide, which is from molecular clouds. And this happens to be a direction where there are no previous observations in the millimeter. It's high latitude. We concentrate toward the plane for those. There's nothing there. So it just means we've got an upper limit. But in all of these cases, the thing that's really important is we've thrown this data point, reliable data point, now on the pile. We have observations planned. There's a whole international campaign involving ARAS, AAVSO, observatories out the wazoo, visual observers, satellites. I mean, it's a very, very nice campaign if everything actually in the end gets coordinated. Otherwise, it'll just be data, and maybe somebody in the future will make something out of it. But the thing that's important about the ATEL is the democratic tool that it represents. I wish it were more democratic in allowing non-professional astronomers to be first authors, and that the communicator has to be somebody who's somehow salaried in this business. But that's life. Otherwise, it would be flooded. And that's what the AAVSO is for. But the difference between the other difference between this outburst of T-core Bohr and the previous ones is actually things like the ATEL. That it's not going, you can think of it this way. In the 1840s, when this character first went off, fast communication was somebody standing on, say, at Le Havre with signal flags, and somebody in the channel signaling back, that there were observers in Indiana who were measuring latitude, who had no idea that somebody in Paris might have seen a nova. Okay? The difference is we know within milliseconds. The whole world will know when any of these events occur. Even in 1987, when the last bright supernova of our lifetimes went off, 87A, it took several hours for the information to get around the world. The fastest was the astronomical telegrams of the IAU, and I remember sitting and decoding one of those. They were literally telegrams. They were sent in code, and the observatories had code books. And that was the fastest way of getting it, and that was only as fast as a telephone. So in some cases, you would literally have somebody sitting on a telephone reading out this code to you. And in other cases, it would come from Western Union. Okay, that was 1987. That's 40 years ago. The whole world knows when anything goes off now. That's a tremendous difference.
Thank you, Steve.
Thanks, Steve. Thank you very much.
I think we can close the meeting. Thank you for your participation. As proposed by Steve, I will send you his email address, and we can continue to discuss the subject and raise questions to Steve. I suggest that this is a collective mail in order that every participant can be informed of the questions and the answers of Steve. The discussion about these and a question onto the white dwarf conduct me to propose you next meeting, if Steve is okay, about a question.
Yes, absolutely.
A question disk, and also the question of what triggered the nova outburst. Of
With
course,
pleasure.
we know something, and all that, in fact, in the context of TCRB next eruption, showing that the things are really complex, and that perhaps we shall have to continue the monitoring for a long time, in fact.
Well, that's actually
Not only weeks or months, but perhaps much more, in fact.
Francois, this is something to emphasize, that professionals emphasize discoveries, and you can emphasize patience.
Yeah.
The contribution of the small observatories is the information that we will not ever otherwise have.
We
There is-
are really amateurs in the sense of we are doing that for our pleasure and not to win a post or money and so on. Yeah, this is the a nice sense of amateur. Yes, okay. Thank you very much for your attention, and thank you very much to Steve. This
Have a
was
very good weekend all.
so interesting and informative and so on. Thanks a lot, Steve. Once again.
Thank you very much, Steve, and thank you for Francois for the organization.
Thank you, Steve.
Thank you.
Thanks, Steve. Thanks, Francois.
To all of you, thank you. And have a good weekend.
Thank you.
Thank you.
Bye.
So I'm gonna go have some dinner.
Okay.
François, merci bien.
Non, c'est moi qui dis merci, Steve. C'est nous tous qui te disons merci.
Look, guys, you've done wonders. I love this.
Thanks a lot. I think we
Hug to the family.
can close now.